All right, legends, welcome. It is Mr. Mays coming to you through the digital wonder that is my iPad and that is the Wi-Fi and that is also our study of statistics in virtual format, your double section study guide. And today we're going to be looking at geometric distributions. It is wonderful to have you here, and I'm so excited to teach you the final aspect of our Unit 4 trajectory, right? This journey has taken us across a bunch of applied probability through different random variables, how to translate, how to combine random variables in interesting and engaging ways, how to find the mean and standard deviation in those variables. We then learned about binomial distributions, and now we're going to learn about geometric distributions. Now, first things first, cast your mind back to when you were in class and pull up the 4.6 notes. I'm going to pull over to slide 3 on 4.6, the geometric distribution notes. And you're going to note that the last question of these 3 available questions on the classwork is, how many Americans would you expect to ask before you encounter the first individual who voted? And we're given a few things. We're given a probability, 66% or 0.66. And we're given a random sample of 20 eligible voters, right, that we are messing about with. And the question here is, well, what are the odds that we encounter? Like, how many would I expect to have to ask to figure out, basically how many would I have to ask before someone who voted gets asked, right? And as we're soon going to learn, 1, that's a geometric question, and 2, what they're asking for is a mean, right, expected value. And the mean for a geometric distribution is 1 over p. So in this case, it'll be 1 over 0.66. And that will be your value. I'm going to check it really quickly to make sure we are all on the same lovely page. Oh, my calculator's acting up. That's okay. We'll roll together. I'm getting 1.5 approximately. So what that means is, if I were to randomly start asking a population that I have sampled, wherein we've learned, 66% of Americans eligible to vote, so we know that it is a sample of Americans eligible to vote. If I ask on average 1.5 Americans eligible to vote, I would expect at that point, at the 1.5th theoretical person, to have met someone who actually voted. Okay. We've got our idea of what the expected value is for a geometric distribution, and hopefully we're starting to understand the difference between a geometric distribution and a binomial distribution. But just to make sure we're clear on this, we're going to slide ahead to slides 5 and 6. Slide 5 clarifies that the big difference between a binomial distribution and a geometric distribution. Binomials have fixed values, right? A fixed value n. Number of trials. I interviewed 20 people. Geometric, on the other hand, we don't need a fixed value. No n. Everything else, however, as we'll see on slide 6, remains the same. We still want independence. We still want a consistent probability, right? And we still need a binary, success or failure, whatever that may look like. Otherwise, they're the same. So the big difference in the 2 things that we should look out for geometric are, what are the odds that I find success on the 4th try, the 12th try, the 1st try? That's a geometric question. And then another geometric question is like the one we just saw, which is for expected value, which is how many people would I expect to have to ask before I get a success? Or how many trials would I expect to have to run before I hit a success? Beautiful. All right. You see that there are a bunch of classwork problems for you to try through. I hope you are testing them out and checking through the slides. Slides 8 and 9 allow you to practice a series of applied geometric distributions. And it is not until we find ourselves all the way forward onto slide 13 where we get to try these out by ourselves. So let's solve these, okay? The key component here is, much like binary distributions, or binomial distributions, I should say, geometric distributions have a function, geomet PDF, and geomet CDF. And it's all about the geomets, as we know. Geomet PDF is for specific exact value. i.e. what are the odds that I find success on the fourth try? And GeoMet CDF is cumulative. Same situation. Oh, wait. Cumulative is 1m, right? Meaning that it goes for from start to the value. What are the odds that I find success within the first 12 tries, including the value? And in fact, because I want to make this well worth your while, I'm going to go through on slide 15, which is, mind you, the same as slide 13, where we're coming back through. I'm going to go through and I'm going to teach you a couple of GeoMet and GeoMet CDF and GeoMet PDF functions, and then we're going to talk about finding the mean for geometric distributions, which we already know, 1 over p, and the standard deviation. Now, the solution for finding the standard deviation is found on slide 14. It is the square root of 1 minus p over p. And remember, 1 minus p is just the odds of failure. So another way of thinking about this is odds of failure square rooted over odds of success. So much like binomial distributions, where we are finding a mean and a standard deviation in a particular way and then using binom PDF and binom CDF, we do the same thing with geometric distributions. We just need to know if we're solving for a distribution that's geometric or binomial or not, and then we apply these rules. Okay, let's do A through C, and then I will run through 2 problems with you and I'll let you go. Okay, research suggests that about 24% of 12-year-olds in the United States can pick out the state of Colorado on a map. Okay, let's go with blue. So we have a probability, it's consistent, 0.24 of 12-year-olds, right? Question A. What is the probability you must sample exactly 5? I'm seeing exactly, so I know it's going to be GeoMet PDF. To find the first one who can pick out Colorado on a map. You'll notice we have no n value, no fixed number. So we know we are not doing binomial distributions. It must be a geometric distribution. So all we need for that is we go to second vars, which is distributions, and go all the way down past normal distribution, past binomial distribution, and we will find, it's like E and F, I think, we will find geometric distributions. And lo and behold, all we need is a value P and then a success rate. And our success rate in this case is going to be 5. We want exactly 5. And you will plug those in, GeoMet PDF, P equals 0.24, X equals 5. Solve that, give me your answer as a decimal, and that is how you do that, okay? That's what I need in terms of work to show my solution. This is for part A. Let's look at part B. What is the probability that you must sample 5 or more 12-year-olds to find the first one? 5 or more. Mind you, 12-year-olds. Once again, I know it's going to be GeoMet, but it's going to be CDF. And I know that because it's cumulative, blank or more or less, etc. We know we're cumulatively pulling together values. Same probability of 0.25. Okay? We want 5 or more. If I think visually, this should bring you back to binomial land. 5 or more is area under the curve, including 5. So what I'm going to do, because I can only do left tail with CDF calculations, is I'm going to find the area up to 4, not including 5, and then subtract it from 1. So I will find this value, and I will do 1 minus that value. Let me make that a little clearer. Right, so I will get my number, and I will do 1 minus that number, and that as a decimal will be the odds, or the probability, I should say, both of which are functional, that you will sample 5 or more 12-year-olds, okay? And that shows up as probability X is greater than or equal to 5, right? Versus this top one was probability X equals 5 exactly. And now we do part C. The wondrous part C. What is the expected number of 12-year-olds you must sample in order to find one who can pick out Colorado? What is the standard deviation? This is us solving for mean, right? Expected value, 1 over p. And standard deviation, which is square root of 1 minus p over p. 1 over 0.24, because that's my rate situation. And I think it comes out to 4.16 people, right? On the other hand, for standard deviation, I'm going to run this calculation. It's going to be the square root of 1 minus 0.24, which is 0.76, over 0.24. I'm just going to pull my calculator out. I've only got my 4 function with me. Love of my life, the TI-84. Couldn't make it today. And I'm getting a standard deviation of 3.63. Okay. So if you can believe it, we are for the most part done. The following things should be very clear to you. 1, geometric distributions are almost exactly like binomial distributions, except, and I didn't say this, except geometric distributions are always, always, always right skewed. Because you have an initial probability of success, and then you have odds of failure on later tries multiplied by those probabilities of success. So the way you find a geometric distribution, in essence, is probability of 1 minus, or I should say, the value 1 minus p, so probability of failure, to some number amount times the 1 success that you're going to get over and over and over again. So the more times you try and fail and then finally get it on the final try, the smaller your odds become. We've learned how to calculate the mean. For that, 1 over p. We've learned how to identify whether it's binomial or geometric with the notion of, hey, is there a fixed number n or is there not a fixed number n, right? And we've learned about different sentence starters that work with Geom, PDF, and CDF, right? Like this idea of Geom PDF is often like, what are the odds that I get this on the 5th try? What are the odds that we get this on the 10th try? Things of that nature, right? And then Geom CDF or Geomet CDF, we end up in situations where it's like, what are the odds that up to 4 successes, or what are the odds that you get success on anywhere from the 1st to the 5th try, or above this threshold, or below a threshold, right? A cumulative function. We've also gone over how to solve for the standard deviation of a geometric distribution. And now what you must do, my legends, is you must practice. Practice, practice, practice. The rules are very similar to binomial distribution questions and functions. So make it very much your point to determine whether it's probability equals, probability greater, probability less than. Same rules with like going 1 less on k or 1 more on k, where k is the number of successes, right? All of this fresh in your brain. Okay. Were I you, I would practice the classwork. You can see the later slides have answers for us. Try out number 16 and number 18. The key here is remembering that these last 2 problems are, for the most part, playing with some binomial questions in mind, okay? You've got this. I believe in you. You are legends and heroes. Thank you for hanging with me for geometric distributions. Look out close, because tomorrow I'm going to be putting up late at night, or not late at night, but tomorrow night, I should say. I'm going to be putting up the Unit 4 pro tips. But this has been Mr. Mays. I am so thankful to have you in my class. Review this material. Shoot me questions on Remind if any of this doesn't make sense. These reminders should feel pretty sensible, though. And hopefully you remember what we did in class, which should buoy these solutions. I am so proud of you. Thank you so much for being my student. And this is me signing off.